Hello everyone. Am I audible?
Yes, you are audible, Supriya. We are going to start now.
Uh,
Agree.
yes, ma'am. Thank you so much. So, good morning, everyone. Welcome to the 13th day of Deep Learning Summer School organized by IIIT Jabalpur. I am Supriya Sharma and I will be your session chair for today. It's an absolute privilege to welcome back Professor Aparajita Ojha, a highly respected academician with over 38 years of experience in teaching and research.
So this has
She had
already
also taken.
I have been introduced,
Okay.
Supriya. No need to introduce again. Thank you so very much. I have already taken one
Yes.
session, so no need to introduce again participants now. Thank you so very much for the organizers for giving me this opportunity. I'm sorry I interrupted you. Let's start if you don't mind.
Yeah,
Yeah.
sure, ma'am. Sure.
Thank you. Thank you. I'm sharing the screen slides. I hope you can see the slides, participants.
Yes, ma'am. It's not visible.
Yeah. Shall we wait for a couple of minutes? Very few participants are there.
I think time we can start.
We can start. Okay, sure. All right. So, good morning, participants. I hope you are having a wonderful time learning different aspects of deep learning. So today we are going to discuss one of the most um, important models which has made sensation in the current years, diffusion models. Uh, with the introduction of diffusion model in 2015 and then it's another view in 2020, now people have understood the strength of diffusion model and several diffusion models have been introduced. So in this session, we are going to have a brief recap of what is meant by generative models, what are diffusion models, and then exactly we'll be talking about the first paper on denoising diffusion models. Uh, well, this is not the first paper. It has origin in 2015 paper, but this is the paper which caught the attention of many researchers and developers, AI experts. Then latent diffusion models, which are also known as stable diffusion. So if I look at the landscape of deep generative learning, we are not talking about generative learning, which is existing since statistical learning. So we are only talking about the generative models in the era of deep learning. So if you see the original like Bayesian networks or restricted Boltzmann machine were introduced in early times, where Bayesian is also kind of statistical learning machine. Then we have variational autoencoder that you studied in this course as well, a variational autoencoder. Variational autoencoders are encoding the given image or given input into a latent space to find out the representation of data. And from there, they learn to understand the variance in data so that they can generate new samples. Then normalizing flows are also generative models which push the given image into the latent space in such a way I would say that they push the image one after the other so that they are able to extract meaningful information from the data, and then they can understand what is the distribution of data. Energy-based models are similar. Energy-based models are mostly dependent on starting with very high energy and then reaching the stability to understand the data distribution. And then autoregressive models also made a lot of sensation. Regressive in the sense that they, from the previous input and the previous output, the current state is determined. So they are more like a autoregressive type. So therefore, they're called autoregressive model. Then in 2014-15, generative adversarial networks made sensation. They were able to produce very high quality images, and I mean, their training of those models were simple as compared to energy based and restricted Boltzmann machine, normalizing flow, and this. So, therefore, they were very much extensively used, and several research papers you will find having different types of generative adversarial networks. Then came denoising diffusion models. And from denoising diffusion model, we have now come out to different types of models which can be called as foundation models. We'll be discussing about denoising diffusion model today. So as a recap, if you see, generative AI is what? Suppose it is a world of flowers and there are images which are there of, so it is image set of flowers. So you have sample images you have taken from the entire world of flowers. You're looking for images. The question is, can you generate an image of a flower that is yellow colored and somewhat looking like this? So, well, from the point of image processing, it was a simple problem. But how do we learn to generate new samples uh, given the data distribution from where we have taken samples? So, can we generate a sample which is lying somewhere here or somewhere here, right? That is the question. So the sample images are basically observations from the space of flowers. You have a huge space of flowers, right, from India to Australia to US to Europe. And within India also, you have plenty of flowers. And let us think of images that are collected from this. And these images can be under different illumination. So think of this. And then the question is, can we generate new images from there? So these are observations. We call them observations. And then generative models help us in creating new samples from the space of whatever objects it is. In this case, it is images from where the observations are taken. So the idea is to approximate the data distribution over a space of objects. So for example, let us consider the data distribution of people in India who are of different age groups, right? So maybe of who are kids below 5 years, then kids below 17 years, then people who are below 25 years, and then people who are below 35 years. And then this is a data distribution, right? So question is, uh, from here we are from the group of people who are below 25 years, below 17 years, below 25 years, or around say 35 years, we are taking some samples, right? And then we are creating images of those people, right? Or their health record. You can take anything. So that is one data sample. So with observed data of samples from an underlying distribution, which is this in this case, this P data, we call it P data. The goal of the generative model is to approximate the data distribution given this very small data set. So there can be, say, huge number of elements in a data set, but we have taken only very small number. So a learned generative model can then be used for inference if we are able to generate this probability distribution or data distribution. So but this we do not have any idea in case of population of India, although you know that people go to house to find out the total number of people below age 25 years, below age 18 years, they are able to find out. But this is an ever growing dynamic data, and therefore finding out the exact data distribution is difficult. In fact, in most of the cases, it is unknown. Like in the class of flowers, we know that the data distribution is unknown. So the question uh, is if this is the data distribution represented here as a point, just point, right? Let us assume that data distribution is somewhere in the space, and we are looking for approximation of this data distribution by making use of some models. This model family can be, say, generative adversarial networks or denoising diffusion networks. So let us consider a model family. From that model family, the question is, can we find out the parameters theta such that this p theta star is closest to this data distribution? If we have any other theta, suppose for another theta, p theta is here, right? That is farther than this p theta star. That is the question. So idea is to minimize this distance, which is between the p data, that is actual data distribution, and the model family from where we are trying to generate the data distribution. That model family can be variational autoencoder, they can be diffusion models, they can be autoregressive models, any kind of models. I hope this is clear to everyone. Just in case you have any questions, please feel free in writing your questions on the chat box so that I would like to answer. So the idea is that distance between p data and p theta star, the one theta that we have found out for which the model is performing best, should be the minimum of the distance between any member of this family, right? Let us find out the minimum. So the minimum, that theta which is giving me minimum, is the desired desired probability distribution that we are looking. So idea is to minimize this distance. So once we are able to minimize this distance, what exactly are we doing with generative models? There are three primary goals. One is, given a data point X, what is the probability of this data point? Like given a data point, say people in the age of 25, what is the probability of like getting this in the entire population of India? If I randomly choose any person, what is the probability that his age will be around 25 years, right? So given a data point, what is the probability assigned to by the model to this data point? So this is called density estimation. Like how many people are within the age group of 25 to 30 years. So that is estimate how dense this population is around 25 years of age. Now, unsupervised representation learning, why? Because so how can we learn meaningful feature representation for a data point? Because what happens that whenever you want to find out similarity, dissimilarity, want to generate something or want to infer something, features or the representation of that data is important. Uh, for example, if I want to find out, say, like how many people in this IIITDM Jabalpur are from, say, how many, this is density estimation, that how many people are from, say, Karnataka region, how many people are from Andhra Pradesh region. If I want to find out the density, then what I will do is that I will be finding out the features from the data of the student, where we can say that the birthplace is any place in Andhra Pradesh. So that is one feature. So how do we learn the features? How does our model learn the feature so that it is able to extract information? From simple databases like the IIITDMJ students record, you can apply simple rule and find out that, okay, in the field of place of birth, or in the field of residence, permanent residence, wherever we have some state or some city of Andhra Pradesh, we'll be able to fetch it. But think of a very diverse data from where we have to learn something. So we need to have to understand the data representation, right? So representation learning is important. Similarly, sampling. So how can we generate novel data points every day? You might be using ChatGPT or any such creative AI models where new data points are generated. But what is the complexity of generative models? In fact, it is very hard to approximate the distribution when the data is from the real world scenario. To give you an example, let us take just a very simple 32 cross 32 binary image, where each pixel has got just two probable values because it is a binary image. So how many different images can be generated? Can you write on the chat box? How many different images can be generated? Each, we have 32 cross 32 places, and in each place there can be two choices, 0 or 1. Can you write quickly? How many different images can be generated? Anyone who will try? I hope you can write. It is very simple question. Who will answer this question? So Kanchan Thakur is saying 2 to the power 32 cross 32. I agree with you completely. Yes, some people are calculating actually. Yes, you're right. So it is basically two places. We can say that there are two choices and there are 32 cross 32, right? So we can see that this is 2 cross 2 to the power 32 cross 32, right? So that means you can see that this simple image is having so many different options. But fortunately, what is happening that we have some prior knowledge about the space of objects. Like the images could be one of the 10 handwritten digits. Like in MNIST data set, we have like 10 hand. So it could be 8 or it could be 7. So when I'm writing, and suppose the background is black and 7 is written by white color, as in MNIST data set, it is very clear that always some of the corner pixels and the edge pixels are going to be black only, right? There's very likelihood that it will only be, likelihood is high that it will only be in a small portion of the image. White colors will be only in a small portion of the image. So like if I ask you, like how many, if I want to plot a dog image, then dog can never be blue color, dog cannot be violet color. They have specific colors only. So the world of different real world objects is highly structured. Like faces are highly structured. Trees are highly structured, right? They can be well defined. So that is what I meant to say. Representation learning. You are representing to learn a face. Like you are learning to understand a face. So you know that a face can be represented by eyes, nose. If you want to make your system learn the trees representation, then tree can be always represented by its stems, leaves, and all those like different things which are visible. So features of dogs and cats are, we can say that they are structured. Therefore, a large number of images is less likely to occur in the data distribution. So when I say how many images are possible from 32 cross 32 image, so actually the meaningful images, although there are 2 to the power 32 cross 32, there is only a very small subset of the meaningful images which can be generated from there. So as a result, the total number of meaningful, like the probability distribution will be mostly concentrated towards some meaningful things. This is what the generative model should learn. So from a very small number of sample images, we expect the model to learn the data distribution instead of giving the prior knowledge. We do not give prior knowledge, but because a child also learns, does not have a prior knowledge. The child comes in this world and learns by observing the world, right? By observing how people are speaking, by observing that how people are expressing themselves, and how what is there around him or her. So right, so it is learning by understanding the world. So coming back to finding out the solution to the problem. So here we have actual data distribution. Here what we want to like find out how close this data distributions, actual data distribution is. Suppose this data distribution, and we have created a data distribution somewhat like this. So suppose this is my p theta star. I want to make it as close as possible, right? So minimum of distance. So what is the representation of model family? First thing is this question, how the distance function is. So first of all, we should find out what type of models are we looking at, which will be the best suited models. The entire research is going on in this direction only. What are the best suited models, right? And then how the distance function between two models is defined. How do we define that this is one distribution, this is another distribution? How do we define the distance, right? How to optimize the distance then? What is the method? What is the objective function? So these are the three questions, and deep generative models are developed to address these questions. I hope this is clear to you. And recall Bayes' rule. Bayes' rule says that the probability of pxy given y is given, so it is conditional probability, given y, probability x given y is the same as probability of x has occurred. What is the probability of y multiplied by this px and divided by py? So what is this? Actually, generative models look at finding out px. If x is the sample, what is the from where the data is coming? What is the data distribution from where the samples are coming? These are known as generative models where we do not have any prior condition. We also sometimes determine generative models, develop generative models which are conditional generative models. Like conditional generative models, like you write a question to chat GPT and you're expecting an answer. So given the question, what is the likelihood of an answer coming from this, right? An appropriate answer coming from this. So what is X given this question? Given this question Y, that what is a diffusion model? What is going to be the expected model? What is the likelihood of the actual diffusion model description that is coming? What is the likelihood that this actual answer will be coming from ChatGPT? So right now, ChatGPT is trained on such a large data set. It has been given enough experience, and therefore it will be giving you mostly most of the questions it gives answers which are quite right. Right. So these are known as conditional generative models. And then we have what are these terms? This is discriminative model. You have studied classification model. You have studied regression models. These are models where you categorize elements in one category. So where given a sample X, what is the likelihood that this sample is belonging to a specific class Y, right? So here, given X, what is the probability of it belonging to a specific class? Or given X, what is the likelihood that, what is the likelihood of its location at this position, right? What is the likelihood of this? And similarly, uh, here, PY is what? It is the prior over labels. So these are givens, priors are given, sometimes not given. So if I look at the discriminative model, they learn the probability distribution, like given X sample is given, what is the likelihood of discriminating them, like Y, what is the likelihood of Y, label Y. In generative models, it learns the probability distribution Px of all samples which are coming, of data distribution from where the samples are coming. And then we have conditional generative models that learns a probability distribution. What? Given Y, what is likelihood of X? As I give you an answer. So how to represent probability distribution? What are the model families that we will be considering, right? Oh, sorry. Um, one autoregressive models that have become very famous, and ChatGPT is also trained in autoregressive way. You can see that here what we are doing, the probability. Now theta is what? The model parameter that we will keep adjusting so that it performs well. So what is happening here, my dear friends? Here what is happening is that suppose the first thing in the sequence is obtained. For example, if an image is considered, suppose first pixel is determined somehow. We know the probability of the color of the first pixel to be red. Then the second pixel will be generated based on the first pixel. Third will be generated based on second. Fourth will be generated based on second, third, maybe previous. So this is x less than I means uh, given x less than I, that these three pixels are generated. One is red color, the other is also red color, the third is blue color. So I find out the probability of fourth being, say, blue color, red color, or green color, and whichever probability is maximum. Let's think about that. So what is the likelihood of xi given x less than I? That means 1, 2, 3 I have occurred. What is the probability of fourth pixel with, say, likelihood of red? So that is p theta will be determining what is the likelihood. And then we keep on doing this for all the uh, for all the successive like generations that you have to make. So somewhat similar to like if I'm speaking, what is the likelihood that the next word will be say word or any other thing. Like in ChatGPT also, you will find that the next word comes. When you write a Gmail also, you will find that some of the words are automatically generated to give you a guess. Like this could be the next word, right? So these are autoregressive in nature. Flow models are, as I told you, that they push the things towards like in this f theta is a kind of invertible transformation. So they keep on pushing data from samples from one representation to another representation, third, and so on and so forth. And for I will not go into details of this, but there is a Jacobian of the transformation that is used. So it's because we are pushing it. So we can say that it's a flowing, data is flowing from one space to another space. What is that space? Latent space, from where we understand the representation of the data. Okay, then we have, so these are all model families, right? Please be very clear that these are all model families that have been proven to be very successful. There are many other model families. I'm talking about these model families which are very extensively used. Variational autoencoder, you have studied last week, where given a sample, from the sample we find out the representation, which is here somewhere. Representations are found out, and in that representation, from that representation, basically what we are learning is, in variational autoencoder, so given a data sample set, data samples are given, right? What is the mean and what is the variation in this data, right? That we learn. And then we create a Gaussian distribution where mean is say mu and variance is say sigma. And from that Gaussian distribution, we sample one point and send it for generation of new sample, right? So what we do is that in variational autoencoder also, you can see that we are estimating density explicitly. Estimating density explicitly means we are trying to figure out what is p theta x and approximating it, finding out, approximating px with p theta x, right? Then we have energy-based model. In energy-based model, we do not consider probabilities, like these are not normalized values. So what we do is that we express this in terms of, like, what we can say is that we think of the model as taking randomly samples where we can have, so we are thinking of data distribution which may be having very high energy, and we try to minimize energy by stabilizing the entire system, right? So idea is to minimize the energy. So this is expressed as energy. These are expressed as energy. And this is what is dependent on e to the power f theta x. And z theta is dependent on theta. So this is known as partition function, because z theta is nothing but the sum of or integral of f e to the power f theta x. And so it is a very intractable kind of denominator. And therefore, energy-based models, although they are also very powerful models, but it is difficult to train them. Then previous sessions, you have studied variational autoencoder and generative, right? So variational autoencoders, as we see, that maximize variational lower bound, right? And here in adversarial, in GAN, we provide adversarial training, where we have a discriminator which detects whether the data is real or fake, and there is a generator which generates data, right? And both of them are working as a competitor to each other, right? That is what is happening. So one is explicit generative model, the other one is implicit generative model. There is a question that how does the distance between p data x and p theta x minimized in these models? So Abdul Makid, there are methods of expectation maximization, or where we find out the likelihood of if there are samples which are given as training data, what is the likelihood of these samples belonging to coming from that data distribution? That is, likelihood is maximized. So this is known as expectation maximization theorems or algorithms, or there are maximum likelihood principles that are used here. So because then only we understand that this is how we can minimize the distance between the model and the original data, where the main challenge is that we do not know the original data. So different methods apply different uh, algorithms for converging their model to the data distribution, so that the new samples that are generated are quite good, in the sense that they are realistic, because we do not know the data generation, data distribution. So there is no clear method of finding out how close we are to the data distribution. So in initial models, deep learning models were dependent on human perception level or human understanding. Later, some evaluation metrics have also been defined, where we understand, okay, that if this is the parameter that is used, then for evaluation, then the model would be good. So we will be coming to that later. Um, So here we can see that one is explicit generative model. What is meant by this? That they actually find out p theta x. And this is an implicit generative model where p theta x is not evaluated, not computed, but we are able to generate samples which are quite high quality and close to the data samples that we have taken. So if I take a comparison of VAE and GAN, VAE, they're very good, but their image quality is sometimes, I'm talking of images because I am from the computer vision background. So let me take image quality. It's a medium, sometimes blurry also. And in case of GAN, the quality is very high, realistic images, but there's a lot of instability in training. Because if you choose a small change in the, say, hyperparameter, then there'll be sudden drop in the performance of GAN. And so it's very unstable. It takes a lot of time in converging also. Second problem is mode collapse. Mode collapse is what? It is producing very good images, but all the images are similar types. For example, I ask it to plot take out a white flower image. Now, white flowers are plenty in the world. They are having a lot of variety, but it will be producing white flower of the same variety. So these are some problems that they have. And if I want to find out what exactly makes a good generative model, this generative learning trilemma is important. We want that the images or the samples should be fast generated. We also want that there should be diversity in data. And the third thing is that we want high quality data. So all three together, it's hard to find out. Like, there are not many algorithms. Actually, we are pursuing in the direction of finding out a model which satisfies all three properties. So diffusion model, that is the topic of today's discussion, have are proven to be very, very like stable in terms of their convergence. Although they are slow, but they can produce very high quality samples. Some of the models, some of the images you can see. So they offer more stable training, high sample quality, and better mode coverage also. Mode coverage means you can see that here people from, say, very different types of color, skin and hair, and a very different kind of eyes. You can see that everything, all smiling faces, but these faces have a lot of variety. You have bedrooms, lot of variety. You have church photos, varieties are different. So I seek your kind attention now on what is a diffusion model. So the essential idea is inspired by non-equilibrium statistical physics, right? What is the idea? Uh, Idea is to systematically and slowly destroy structures in a data distribution through an iterative forward diffusion process, right? So let me now write completely. So first is that we are making use of a non-equilibrium thermodynamics, which is and we are slowly destroying the structure in a data distribution by iteratively forward diffusion process, iteratively making use of a forward diffusion process. And then we learn the reverse diffusion process. Just like a jigsaw puzzle, you simply destroy the combinations, right? And then you expect that the child or your opponent should arrange them to get a meaningful output, right? So we then learn a reverse diffusion process that restores the structure in data. So how do we learn this reverse process? So first the data is given, we destroy the information in data, and then we again try to rearrange them, right? So what is important is yielding a highly flexible and tractable generative model of the data. Okay. So a system in thermodynamic equilibrium, think of a system in thermodynamic equilibrium transitioning between two states, right? Can be described. So transitioning between two states, here is state one, say, suppose there is a ball, state one, and suppose here is state two. Ball reaches here to here, right? So can be described in terms of difference in free energy, right? I hope you remember what is energy. So non-equilibrium thermodynamics. So one is what? Equilibrium, system in thermodynamic equilibrium, right? Like we have equilibrium between temperature, pressure, right? Everything is in equilibrium. It is transitioning between two states, can be described in terms of difference in free energy, right? But in non-equilibrium thermodynamics, we like, is it possible to express this in terms of difference in free energy? That was the question that was bothering people working in the area of thermodynamics. So the non-equilibrium thermodynamics deals with systems that are not in thermodynamic equilibrium. And you can see that most natural systems are not in thermodynamic equilibrium. You cannot expect that pressure, velocity, every day you see that weather is changing. Lot of like air pressure is different, temperature is different. So, and change is happening, but that is not in equilibrium. You can see non-equilibrium conditions many cases. So the straight transition in equilibrium refers to changes in a system's properties while it is in the state of equilibrium, right? Uh, so in an equilibrium state, what happens? The system states like pressure or temperature, concentration are uniform, like they do not change over time when isolated from external entities, right? Just think of a simple plain water kept in a glass. So external quantities can be temperature, external temperature. It can be anything, right? But microscopically, particles keep moving due to thermal energy that is present inside the volume, right? So you can see this Brownian motion of fluorescent latex particles in water that is showing it's like water is still water, but a lot of energy, like transition from one state to another state, that keeps happening. So taking the idea from here, let us assume that the transition from equilibrium state A to B is governed by a probabilistic evolution of a system's microscopic configuration. So overall, there is no change, but some changes is happening at a microscopic level. So that can be expressed by what is known as a diffusion process, right? My sincere apologies because of some network problems. I was disconnected. I will again share the things. So we were talking about, say, system which are in equilibrium or non-equilibrium state. So there was a lot of discussion, like when people were studying thermodynamics, equilibrium states, and non-equilibrium states. So what happens, I seek your attention here. You must be thinking that I'm talking about AI and why I am talking about now thermodynamic equilibrium. My dear friends, in the current scenario, you'll find that Nobel Prize in Physics was won by an AI scientist. Why? Because he used principles of physics to define the current AI methods. And they used both of them, like John Hopfield and Geoffrey Hinton, and many new ideas from physics and other domains are emerging to understand to better understand methods that we can develop for AI. So the transition from this can be expressed by diffusion process. If suppose is not in equilibrium, external. This will describe stocking glass where the temperature is almost kept the same. There are external things that may equilibrium state may be disturbed. So Zarsinski's I think N is present here. I've forgotten N perhaps. Showed that the transition between two equilibrium states A and B can be described by average exponential of the work done when the system transition takes place from state A to state B in a non-equilibrium manner. So he could connect the transition between two equilibrium states and the transition under equilibrium, transition between two states under equilibrium and transition between two states under non-equilibrium states, right? He could connect that. So he used an equality showing that this is the equality where what is this is basically exponential of the equilibrium free energy difference. This is the difference of free energy, exponential of that. And what is this? This is the ensemble average over many realization of non-equilibrium work. So think of taking many instances and take their average, right? And here W is the work done on the system during non-equilibrium process from state A to state B. This is your W. And gradient like this delta F, which is FB minus FA, is the difference in the free energy between the final equilibrium state and the initial equilibrium state, right? So what is important here is that this is equating equilibrium state with a non-equilibrium state, right? Some kind of relationship he could find. So here, what is beta? It tells how sensitive the system is to energy changes, this beta. With T as the temperature and Kb is known as the Boltzmann constant. And at temperature T, each particle has an average energy, say roughly kBT, where like temperature is converted to energy, making use of this Boltzmann constant. And this is calculated by repeating the non-equilibrium transition multiple times. Okay, I hope this is clear to you. Now, actually, the entire diffusion process model is based on this. That is why I chose to define this. So, connection with generative modeling. Can we estimate a complex data distribution from where samples have been obtained, starting with a simple data distribution like Gaussian? So, the question is, can we make state changes in such a way that the state of equilibrium can have some connection with the state of non-equilibrium? So the principal idea of denoising distribution model is this, that use a Markov chain of diffusion processes to gradually convert one data distribution into another, starting from a simple distortion, right? To a simple distribution, a small distortion, until the target distribution is accurately estimated, right? That is the idea. I hope this is clear to you, that we are looking at the population of India with health indices of each population size, like from what is the health index from 0 to 5 years people, 5 to 10 years people, in different regions. Like in Mumbai, the health index may be different. In Uttarakhand, the health index may be different. So we are looking at the health indices, like we want to model the health indices data, right? So what we are doing is that this is a very complex data, but we will start with a very simple Gaussian distribution, that health index for most of the, say, 25 years age, and health is most, like health index is high. People who are older, their health indices are low. People who are children, children category, the health index is low. So we start with a very small, simple model, and then we would like to see. So transition from simple to complex distribution, this is a very simple Gaussian distribution, and we apply perturbation step by step. So diffusion process will be applied. Then we obtain the target distribution. That is the idea. Okay. So what is a Markov chain? If you have not studied Markov chain, just this is a brief recap of Markov chain. It is a stochastic process where, like, say, weather is a random variable. Weather can be expressed by several random variables like temperature, humidity, then cloudy, non-cloudy, where different types of things are there. So weather is a vector, we can say, which has several components, and each component is a random component, right? So this random component can occur randomly, like sunny, cloudy, can be two components, two values of this component. Temperature can take value, say, from 30 degrees to 40 degrees in summers, right? And so there can be some random values that are attained by each component of this random vector. So it says that a stochastic process describing the sequence of possible events in which the probability of each event xt at time step t occurs, that depends on the state attained in the previous event. Like if the temperature yesterday was lying between 30 and 40 degrees, then temperature today will not be suddenly from 0 to 8 degrees. So it will only depend on, suppose the temperature depends only on what happened yesterday. So what was the state that was attained at the event xt minus 1? Accordingly, the today's state will be changed. So assume that the probability of train reaching a station at scheduled time is dependent only on the state that the train reached the previous station at a scheduled time. The event is here train arrival, and the state could be, say, on time or late. There can be two states. Another example, let's take weather forecast. The chance of rain tomorrow depends on today's weather condition. So let the probability that it will rain tomorrow, if it rains today, be alpha, and it will be rain tomorrow if it does not rain today, be beta. So state is 0 when, let us assume that, let us call state is 0 if it rains and state is 1 if it does not. Then this is a two-state Markov chain with the transition probability matrix given by, say, from 0 to 0, like alpha. 0 to 1, it is 0 to 1, say, it is 1 minus alpha. When it rains, state, so if it rains, if it is raining today and tomorrow it will also rain, is suppose alpha. So not rain will be 1 minus alpha. Also, suppose it did not rain today. Suppose this is beta, the probability that it will rain tomorrow is, say, beta. It will not rain tomorrow will be 1 minus beta. Suppose this probability is given. So we can define the Markov chain is in kind of a graphical model. We can define this in terms of a graph. So from rain to no rain, the transition probability from rain to rain is alpha. Transition probability from no rain to no rain is 1 minus beta. Transition probability of rain to no rain is 1 minus alpha. And from no rain to rain is beta. Right? This is how it is expressed. I hope this is clear to everyone. Is this clear? Shall I go ahead or you have any questions? If you have any questions, please feel free in asking, right? Okay. Okay, thank you, Binny Thomas. All right. So Markov diffusion process. Now what we are looking at in diffusion model is Markov diffusion process. So in the context of diffusion model, we start with a very simple Gaussian distribution. Let us call it as a QXT. That we assume that this Gaussian distribution model is obtained after, say, um, uh, making certain transformations on the initial model, right? So several transformations like T times some diffusion has been like something has happened. So we start with this QXT. Then we keep on making a small perturbation to original density function at each step, like assumed to be obtained. So we start adding some noise here. We start adding some noise here. Keep on adding noise here. Finally, you arrive at this distribution. So we say what we assume that this QXT is obtained by adding a small perturbation to the original density distribution at each step. So it was this, and this was changed this was changed to this, and so on and so forth. And finally, because Gaussian distribution is a simple one to work with, and therefore we will be starting with a Gaussian distribution. So I hope everybody knows what is a Gaussian distribution. Then we use Markov diffusion process at each step. We make use of that to gradually convert one distribution into another. At each step, what we do is that we attempt to obtain a better approximation to the target distribution by making use of Markov transition process. So diffusion models are latent variable models. So they are actually trying to figure out what is the latent variable. And a denoising diffusion model learns to generate new samples in 2 steps. What? There is a forward process. So given a sample, a forward diffusion process is applied that gradually increases noise in the input. Okay. By adding the noise step by step. It's a forward process, right? Adding noise. That means we are just like destroying, just like in thermodynamics, non-equilibrium and equilibrium case, we are destroying the equilibrium situation, and then we would like to come back to equilibrium situation. So the reversal processes, it learns a reverse, that is denoising process, to generate data from a noise sample. Do you remember, my dear friends, when you started with GAN, that you start with a noise sample and then you generate new data? So the question is from where this noise is generated, right? Right, from where we got this noise. So what we are doing is that we are at each step, we are adding noise, and finally we arrive at a step which is a latent representation of the original image, where we have sufficient amount of noise, but we have a hidden latent variable there. So from that noisy data, we are trying to learn how to subtract the noise. We have added noise, how to subtract noise, right? So the data is this in the fixed, which is a fixed process, which is not learnable process. forward diffusion process, we are like transforming the data. There's no learning parameter here. So we keep on making use of a Markov chain. So it's a fixed already, like in Markov chain, transition probabilities are defined, suppose in advance, then accordingly it will be changing. But in mind, I seek your attention that in the reverse process, which is a generative process, we are trying to figure out how to denoise this noisy input. So forward diffusion process is fixed, right? And reverse diffusion process is a learning mechanism. So what do we do in forward process? In forward process, we have T steps. So we make use of, say, x0 to xt, we make use of a noise like noise Gaussian distribution, from where we add noise, then another, then the third, and so on and so forth. We reach xt in T steps. So the forward diffusion process gradually adds noise to data according to a variance schedule. Remember that variance schedule is defined, right? This variance schedule is taken, like this will be beta 1 and then beta 2, so that there is a variety that is there, right? And in the reverse process, like here you can see that the forward process is given. So you can see that qxt, now qxt, that is likelihood of previous, this was the previous image. What is the likelihood? Like this is the conditional probability. So this is the conditional data distribution, probability distribution that I'm defining, is equal to the normal, that is Gaussian distribution, with center at xt, and xt has been chosen with center. You can see that 1 minus beta t xt minus 1, this is my center, right? And the covariance vector, covariance matrix or covariance vector here, because I have taken here a diagonal matrix, a identity matrix, and multiplying by beta t. So this is my covariance matrix, and this is my center multiplied by xt minus 1, right? So this is my center. What is the like conditional probability of xt occurring given xt minus 1 here? And so I'm making use of a Gaussian distribution. This is what is here. This Gaussian distribution with center at this position, and covariance matrix as this position. Is this clear to everyone? That we are actually building this transition, which is, you can see that can be expressed, which implies that Q, like joint probability, let me delete here, or the joint probability you can see is obtained as, like, what is joint probability, my dear friends? What is joint probability? Can you just recall what is joint probability? Anyone who would like to tell what is Q1, X1, X2, Q, X1, X2? What is joint probability? Hmm? What is the joint probability that, yes, please. No, not always multiplication, Chandrakant. Not always multiplication. What exactly is joint probability? Of two events happening together, isn't it? That is joint probability. If they are independent, then this is multiplication, right? So Prathamesh is also telling, like, QXY, QY, he's making use of some Bayes rule. Joint probability means just don't, I mean, look at the formula only. Imagine that what is joint probability? Joint probability is that me coming in white dress and my friend also coming in white dress. This is joint probability of this event, that me and my friend both have put on white dresses, right? That is joint probability, which is totally independent. If I did not discuss with my friend and he also did not know, then the probability of occurring together, like both coming in white dress, is independent. In that case, it is multiplied. Like joint probability, if the x1 and x2 are not independent, identically distributed, then this will not always be totally multiplied, right? So joint probability is the two events happening together. They can be dependent on each other, they can be independent, right? So some more answers have come. Two events happening simultaneously, I agree with you. Same point at time, agree with you, Lakanlal. And there is joint probability is the probability space of two or more events that affect an outcome. There's nothing like outcome here right now. Of course, I agree with you that outcome is affected in case of this specific example. Yes. Now, so you can see that here I have written what? Probability, joint probability of more answers are coming. Thank you. No, Abdul, I will tell you, like, if you remember in the thermodynamics, what was there? Beta was what? Beta was actually, if you remember, they have taken from the same idea, beta. Beta is taken from same idea. Just go back to. If you see, beta, just give me a minute. I request you to please recall that right? How sensitive the system is to energy changes. So beta is a basically each particle has an average energy of 1 upon k beta t. So it is 1 upon k beta t, inverse of the average energy. So that is why it tells you how like sensitive is the system. So that is the idea that we have taken from there. And from there, we have arrived at this, right? Just a minute. Right? Is this clear to you, Abdul? Yeah. So this is actually inverse of the average energy that we are having. So it is inverse of that. Okay. Now, so so we have taken it from there only, right? So what is happening is that we are trying to figure out what is the joint probability of Q1, X1, X2, Xt given X0. This is the sample which is given. What is the joint probability, right? So this is how it is represented here. In this case, it is product because it is independent because these like noisy parameters are all independent, like beta 1, beta 2, right, beta t, they're all independent. So this will be independent. So can we obtain a closed form solution of q xt given x0 at any time step? Is it possible to find out a closed form solution? That is the question, right? So the formal definition of pass is this, right? We have we are adding some noise every day. So the question is, can we jump from here to here directly? We want to find out qt given x0 at any time step. These are all independent, beta 1, beta 2, are they independent, right? Actually, it is possible. Why it is possible? Closed form solution, find out explicit. You can explicitly express it in this form. Like, how do we express a plus b whole square? It is a square plus b square plus 2ab. That is the explicit form, right? That is the closed form solution. So it is possible because a forward process, in the forward process, how, let us see, we can sample xt at any arbitrary time step in closed form. Why? Because in the reverse process, we would like the model to learn that if at any time instance, the denoised, like some kind of noisy input is given, how to denoise that at any time step. It could be t can be 5,000, t can be 1,000. And at any time step, if you know what is xt, you could actually denoise it, right? So to see, let us set alpha t is equal to 1 minus beta t. Then xt can be written as what? Xt, if you remember, xt was belonging to, just go back to this, right? This expression. Here, this expression is what? Q xt, Q, sorry. This expression is like q xt given xt minus 1 is this. So xt can be expressed as, so this is center, right? So you have here, this is center, 1 minus beta t xt minus 1. And here is what? Variance. So because of the variance here, you will be again taking what? Under root beta t, right? So that is why I am telling that this is possible. We can write xt as under root beta t, which is like 1 minus under root alpha t. And what is this? This is the noise parameter, right? You are choosing variation. This variation is there. So this is my center. And this is a small variation. That is a small noise that is coming. So here what is happening is xt is equal to under root alpha xt minus 1 plus 1 minus under root 1 minus alpha t et. So it was initially xt was equal to under root 1 minus beta t into xt minus 1 plus beta t under root. And then here I'm using this small variance, that is noise that I'm adding here. So this beta under root beta t is 1 minus under root alpha t, and beta t is 1 minus under root beta t is written as this. I hope this is clear to you. So xt minus 1 can be written like this, then xt minus 2 can be written like this. You go on and then you get x1, right? So substituting these values, like you can substitute xt minus 1, you can substitute in xt minus 1 this xt minus 2 and this sum. If you keep on substituting iteratively, you will be, so recursively you can get this, and finally you get that k varying from 1 to t alpha t is equal to, I will, let me explain, let me express this as say alpha t barred. So you can see that, let us take c x2 is equal to root alpha 2 x1 plus root 1 minus alpha 2, say epsilon 2, E2, right? Now you can see that what is multiplied by x0? X0 will be multiplied by all these alpha 1, alpha 2, alpha t. So that is what is there. Is this clear to you all? Can you understand what I am doing here? I am simply like substituting here. I am substituting, say, in place of xt minus 1, I am substituting this expression. In place of xt minus 2, I am substituting the next expression. I will keep on doing this. So what will happen that xt minus 2 will be multiplied with alpha t and alpha t minus 1 under root. And keep on going down, you will see that x0 will be multiplied by under root alpha 1, under root alpha 2, and so on and so forth, which is what I have written here. So this is product of all alpha k varying from 1 to 2 into x0, plus here something which is not dependent on x0. So I express this as a noise. So this also can be proven very easily, making use of a principle of induction. So I'm not going into details, but xt can be written like this. Is this clear to you what I have done? Is this clear to you what I've done? So in a way, we can see that qxt given x0 can be written as a Gaussian distribution of alpha t under root x0 plus 1 minus alpha t I. Is this clear to you? See, it is a little mathematically involved, but you will have to understand that how things are moving. So in the forward pass, samples are taken from an unknown distribution. That is what I was explaining, Abdul. What is alpha bar? Alpha bar is product of all alpha 1 root, alpha 2 root, alpha 3 root, alpha t root. All multiples of like original sample is x0. So you would like to see how at any time step xt, at any time step, the question is, can we express at any time step xt that is obtained from x0? Answer was yes, because what we did was that we wrote xt in terms of xt minus 1, xt minus 1 in terms of xt minus 2. And we took the product of when we substituted, what is the product of all the coefficients that we obtained is what is alpha t bar, right? You can see that that was there, right? Exactly the same thing is what I have written there, right? Is this clear? Hmm? So perturbation is applied step by step to obtain what? Gaussian distribution. So idea is that actually it was the original sample which was coming from a very complex distribution, unknown distribution. We kept on making it noisy to ultimately last will be what? X capital T will be a Gaussian distribution. Come back to this. See down here, you can see this last equation. This is a what? It is a Gaussian distribution, right? Gaussian distribution dependent on original sample and some value, which is parameter, right? This parameter is fixed, right? Okay. So perturbation is applied step by step to obtain a Gaussian distribution. So the variance schedule here is designed in such a way that alpha t tends to 0. What is alpha t? Alpha t bar is product of beta s, s varying from 1 to or t maybe, right? This is my this. So I should be able to design beta s in such a way that this should ultimately tend to 0. Why ultimately 10 to 0? You can see this. Go down, you can see that ultimately this is, if this is 0, this part, let me use a different, see in the bottom, this part is 0, right? So, and this part is 1. So ultimately what will happen? That this will be a Gaussian with center 0 and covariance vector as identity matrix. Thus, in the forward process, x0 to xt is a Markov chain adding Gaussian noise at each step. In the reverse process, xt to x0 is another Markov chain. Now, forward was fixed. We are making beta t fixed. Now, reverse Markov chain is learned Gaussian distribution. With pt that is starting from xt, which is sampled from 0, 1. That is, I take simple sample from 0, 1. Remember, in GAN also, they took a sample from noise sample from this Gaussian distribution. But this time Markov chain is learned to remove noise. Initially, it was adding noise, and now in the reverse process, it is removing noise. We start by sampling this from N01, and the model learns the distribution. What is the distribution given xt? What is xt minus 1? So it keeps on doing that at each step. Where xt, like this is the center, is computed using a noise predictor network. So here comes the importance of neural network. That is typically a UNet kind of, or ResNet or transformer based model. UNet model was initially introduced for biomedical image segmentation, where like images were downsized mostly, or features were extracted, and then they were reconstructed with segmentation mask, right? So UNet like structure. ResNet is a residual net which made sensation in 2015, around 10 years ago, because of very deep network of 152 layers, and it was able to produce the same, like better human perception level in identifying images than an average human. Transformer based model we have already studied. So what is this forward process from xt to xt? We are looking at what is the likelihood of getting xt minus 1 given xt, like unnoised image, and where we have already computed xt from xt minus 1. But this is not known to the learning network, because the noise is obtained, like we are sampling from this. The question is, how do we get this? So the network does not know like xt from xt minus 1, right? Remember this. So initialize, what is done? First, we initialize one sample from N01. We keep on sampling this from like mu theta xt sigma square t this. So this is what is learned, my dear students. This is learned. At t is equal to 0, sample x0, which is the final generated image after you learn all these noise removing values. In the original paper by Ho et al., the authors have used a UNet backbone similar to the unmasked pixel CNN plus with group normalization throughout. So training in Ho et al. Paper is performed by optimizing the usual variational bound on negative log likelihood, right? So here it is log likelihood that is taken here. We have, after some mathematical computation, we can write it in terms of divergence, KL divergence. Somebody was asking that how do we estimate? So KL divergence is one method that is used. For this, KL divergence basically is looking at what is the divergence between two samples. It looks at the divergence. So it tells that how diverge, like what is the divergence between the probability of xt and the probability distribution of xt given x0. Similarly, what is the divergence of probability distribution xt minus 1 given xt and x0, and probability distribution of xt minus 1 given xt and this. So then the authors actually derived from here to here, which I'm skipping. If interested, you can find in the paper, which is mentioned here. Here, this EQ is what? EQ is the expectation, right? Expectation is, in crude terms, you can call it average over the samples from the distribution Q, and DKL denotes the KL divergence. Okay, so training in the training time, we take a sample from the data samples, and T is uniformly taken from 1 to T. And I told you that XT can be formed from X0, right? So we take a noise sample, noise value from n from 0 to, like, from the Gaussian noise, it's centered 0 and this. And then this E theta is what? It is learning to remove noise, right? So it is trying to find out what was the actual noise between x0 to xt. What was the noise? So that E theta is basically learning noise. It is the output of a network which has learned noise, and the idea is to find out the minimum of the distance, I mean, minimize the distance between the actual noise and this sampled noise, right? So it learns until converged. In sampling, all that you have to do is to take a sample, noisy sample, and we keep on removing noise, right? We keep on removing noise, subtracting noise. That's all. And finally, after T steps, you return X0. So intuitively, in the forward process, we add noise to an input, and in the reverse process, the model learns to predict noise and subtract it from the input to denoise the input. All right, that is the idea. Basic idea is this. So note that the forward process is fixed and there's no learning parameter. But when they introduce this idea, they introduce 1,000 steps for all experiments, and they set the forward process variance to beta 1 is equal to 10 to the power minus 4, that linearly increasing from minus 10 to the power minus 4 to beta t is equal to 0.2. So it's increasing. And these constants were chosen to be small relative to the data that was a scale between -1 to 1. Diffusion models, most of the diffusion models that we have learned, they use the resonate block or self-attention layers also in the unit architecture. So this is what is a typical architecture, typical network structure. So here you can see that the time is also, as you can see here, time is also embedded, right, through fully connected layers. So if you remember, I told you that we do not know what was the time step on which a noise was embedded, right? Eta t supposes the noise was embedded in x0. So from x0 to xt, how did we reach? Accordingly, we want to, like, not only epsilon t, that is important to be determined at what time step. So The time representation is done using sinusoidal positional embedding or random Fourier features. And the time features are fed to the residual blocks using either simple addition or adaptive group normalization also, right? So Juhi is asking, we will produce a noisy vector first using a diffusion model and then use it to give a GAN. No. Juhi, you have to, if suppose you have a trained model on data samples, suppose you have 5,000 samples of flower varieties, you will be training this by injecting noise step by step using a Markov process, right? Where Markov process is what? It only depends on the previous like state events, previous event, right? So what at time step t, what is the event is dependent on the previous step events, right? So at each step you are having a, so if you remember, I told you that at each step we are making use of a Gaussian distribution from where we are taking out noise based on the schedule beta t that was there, based on the schedule beta t, right? Noise adding schedule that was given, right? Based on this, we had a normal distribution or Gaussian distribution from where we injected a noise. And then after the training is done, so that it learns, like we inject noise and present a noisy sample to the network. This network will learn to subtract noise from here and finally arrive at a clear output. That is, which is a clean output, I should say, right? It should take out a clean output. So when the model is learned, trained, you simply need to sample. That is what I told you here, right? Here, what is this? When sampling is done, what are you doing? You are sampling from noise, like from Gaussian distribution, which is centered at 0 and having identity matrix as the covariance matrix. You simply choose a vector. You can randomly select a vector from here or an image from there, and then you can create new samples, right? So Juhi was asking this. We are not giving to GAN. In samples, we remove the noise from the input, and in training, we learn to predict noise, right? In training, in sampling, we remove noise. Yeah, we remove, because we have already learned to remove noise. So in training, we learn to predict noise, and when we sample, we actually are removing noise. Yes, I agree with you, Prathamesh. I hope this is clear to everyone. So what makes a good generative model? We come again. Generative learning trilemma is like, we have three important objectives, three important goals: high quality samples. There should be diversity in the samples, and sampling should be fast. I should not be waiting and for long training hours, and then of course after long training hours the samples that are generated should be fast generated. So GANs are good at this. These two, they're producing high quality samples, fast sampling. But if you remember, I told you that mode collapse is the problem. They are generating similar type of images. Variational autoencoders are very good at fast sampling and mode. They produce a lot of diversity, but the images and samples are often blurry. Denoising diffusion model at the end, after all this, these things that we have done, we have still not been able to achieve fast sampling. Of course, high quality samples, high resolution images, lot of diversity in images, everything is done, but still we are not reached. So then latent diffusion models were introduced. What are these? These Rombach and others they studied diffusion models comprehensively, and they came out with a solution because they found that these are computationally expensive, high resolution image synthesis is very highly computationally expensive because you are doing sequential evaluation and inference is also slow. So they applied diffusion models, applied in the latent space of already pre-trained autoencoder. So think of a pre-trained autoencoder you are training. I hope you have already done a session on this. How do we train autoencoders? So let us pre-train, let us have a autoencoder. So autoencoder is pre-trained. That means it is able to understand the features of the data. It is data representation model. So it will be learning the data representation. So we start from here. Rather than from image, initial image, we are looking for much lower dimensional feature of image, which is learning the representation of the image. So training diffusion models, such a representation contributes to complexity reduction because instead of say 512 cross 512 image, you may be just having say 7 cross 7 cross some 16 size output, right? So this is computationally reduced and also preserves the detail because the trained autoencoder has learned the features. So then they have introduced cross attention layer. Like in transformer, we have attention layer. They have used the same thing into the model architecture. Instead of like ResNet, and then they have also used attention layers. But here they make use of cross attention layer. And so they have made very powerful model. But then one thing that they've added is conditional input. Like in conditional GAN, we have what we have? We have the input along with some condition. That it condition can be class label, the location, any condition. So like bounding box can be location or text prompts, like I want an image of white rose. So that is a text prompt, right? So methodology is what? Step one, we compress images to latent space by training an autoencoder. Normally pre-trained VAE is used to compress the input image to high resolution, of a high resolution to a representation space. Then we apply diffusion model, the same model that we have used, to latent representation. Forward process of adding noise is the same as discussed earlier. In the reverse process, the noise learning model is trained to minimize this. What is this? This is the actual noise that was added and the learned noise, right? Square, that this is known as the mean square error, where 2 here shows the L2 norm is used. L2 norm is similar to what we use in a Euclidean norm, like in case of discrete, it is say x1 minus x1 prime whole square plus x2 minus x2 prime. These are component x2 prime whole square and so on and so forth square. This is the L2 norm of x minus x prime, right? L2 norm square. This is the same as this here. And what is this? Let me tell you. So with a conditional mechanism, like the model, if you want to have a conditional mechanism also, then you can choose the loss function as this. E minus E theta, here is the conditional. Y is the conditional here. So let me explain what are these quantities. So condition can be a text prompt, a sketch, or anything. So let me explain what are these ones. This is an autoencoder. So X, from X, I transform it to say Z, right? Autoencoder. Then Y is a conditional that can be a sketch from where you would like to generate a realistic image. It can be a text prompt. It can be a location, anything. This is the noise that we are basically sampling. And you know what is this time step? This time step. So Juhi Paridi is asking, in latent diffusion model, the latent vector is obtained from VAE, then we apply diffusion model. Yes. Instead of X, the original samples, to train the model, not to sample. To train the model, we are first downsizing this so that it is able to learn the representation. So significantly, the computational complexity is reduced, because if you want to apply a convolution on an image of size 512 cross 512 or an image of size 32 cross 32, there is a lot of difference, right? Computational complexity is reduced. So now see, what is this? This is domain specific encoder that projects Y to an intermediate representation. This is that clear to you? That we are actually also encoding what? Another prompt along with that. Okay. So uh, is that clear to you, that what we are doing? So this is the loss function. This is the loss function that we are using. Oh, sorry. Okay. All right. This is the loss function that we are using. So model architecture is also not very difficult, but let me seek your attention to help you understand. So if you can see that, what is this? This is an encoder, right? X is sent to an encoder. So you get the latent variable, latent space representation that passes through a diffusion process, right? So you get Z, from Z you get ZT, that is Markov chain of diffusion process of adding noise, ZT. Then this ZT, along with this, you can see that we have a conditional. This conditional can be semantic map, text, representations, images. They are passed through a encoder that encodes them into, like, to a, like we basically make use of encoder model so that it can be encoded along with ZT. So with ZT, you can see that it is encoded. Then it is passed through a diffusion unit, where what is E theta? E theta is diffusion unit, which is learning to remove noise or subtract noise from the actual image that we want to find out. Okay, so you can see that in this unit, it is this cross attention layers are also used. These QKV, if you remember, transformer models use a query key and like value vectors. These are embedded, right? And you also see that this is also passed through this ZT minus 1, right? So denoising is done at each step. So this is the denoising step, which is denoising from ZT minus 1 to ZT and so on and so forth. Finally, this denoiser, you can see that this encoder, from this autoencoder, decoder is used. This was encoding, this was decoding, that is used, and finally you get X wave. So X was the original image or original sample. X wave is the final sample that is obtained. The idea is to minimize the distance between this, and that is what we are doing. So generated images are very high quality images, as you can see here. It is also text to image synthesis it is doing. So a painting of a squirrel eating a burger, you can see that very good image paintings are given. A watercolor painting of a chair like that looks like an octopus. So quite like reasonable. And it says that a shirt with the inscription, "I love generative model." So you can see that the shirt are also realistic images that are coming. So text to image where conditionals are given. It has also shown image super resolution application like bicubic. If you use super resolution bicubic interpolation, then it gives you this super resolution. If you use here latent diffusion model, super resolution, then it is giving this. So it is giving you better super resolution as well. Also, in case of image in painting, where this was removed, this was all removed and occluded, and you want to regenerate that. So that also is very much done. These were all done initially using image processing methods. But you can see that now it is learned. So for any new thing, it will be automatically generated. So this is what I generated this table by ChatGPT to let you know that there are some popular text to image diffusion models. Delhi 2, you know already. Then stable diffusion is the one which is initially was known as latent diffusion model, but then Stability AI launched that as stable diffusion. Then Imagen, then Glide. So these are all developed by, say, Stability, Google Research, or big giant companies in this direction. But the pursuit to achieve the three goals is still on. We are having fast sampling in some models, but they can be very blurry and not as we desired them to be. There can be mode collapse, like in GAN. There is a lot of diversity that is introduced over the similar later type of GANs, like style GAN, introduced by NVIDIA, or we have cycle GAN. Several solutions were given, but still mode collapse is a problem. There's no diversity. Images of high quality GANs are producing. Now a combination of GAN and diffusion models introduce a combination. So you can see that like inclusion of noise and then exclusion of noise. You can think of this as a denoising autoencoder model, which is equipped with the idea of diffusion process, Markov chain diffusion process. But it is slightly different than the diffusion model, denoising autoencoder, because you know that in denoising autoencoders are trained differently. So there are various methods that have been like hybrid approaches have come up. And in summary, we can say that the diffusion models are based on the principle of non-equilibrium thermodynamics. Very simple idea was taken where there was a scheduler that was given, and that scheduler also helped us in, like in my Markov chain, you know that from the 0th step, if we know the transition probabilities, they're fixed, then you can reach up to the tth step directly. So at each step, we are injecting noise and making it very noisy. And now we are expecting the model to learn how to denoise the data, right? So at any step, time step, it may be having a noisy image of any time step. And therefore, it was important to jump from x0 to xt to know like how we reach from x0 to xt. And so at any time step, it learns to like subtract noise. It is simple to understand and implement. Although image quality is impressive, they are slow in sampling new data. That is the greatest concern. The latent diffusion model present a simpler and efficient way to significantly improve both training and sampling efficiency without degrading their quality, image quality. They're efficient in text to image, image in painting, and different types of conditional image generation. If you remember, I told you initially that there can be models that are purely finding out PX, that is data distribution. So these are generative model which no prior conditions, generative models, right? Models with no priors. But there can be generative models with the priors. Like we have prior, this can be a text, and you from the text you want to generate an image. So different types of conditional image generation. These are conditional generative models, right? Extensive research and development is going on in the direction of diffusion models and in general on generative models. With this, thanks. If you have any questions, please feel free in asking. Else we all end the session. So the question by Prathamesh is, are the diffusion models the latest architecture? Meaning that there are no newer, more efficient architecture discovered as of yet, kind of state-of-art techniques. There is a difference between architecture and models. Architecture is a network structure, is a component of the entire model. You can use different network structures to improve the quality of a model. So model is what? Given a data, how can we design the entire method, a model, to represent that data, right? Or to infer from that data, right? That is the model. So model is having several components. One is network structure, and second is training methodology. So here the training methodology along with the network structure creates the entire model. Diffusion are the state of the art. These are the newest type of models that have been introduced. And if there's no discriminator here, how does the model ensure that it is being trained on a correct data? A very good question, Abdul. But data is correct. It's trained on correct data is correct, because data is coming from real world. So data is trained, but data is correct. But it is how it is learning is something that only earlier humans could understand that, yes, this is learning well. Like when we say that the image captured is very good, my eyes may not be that good in understanding the small vibration that has occurred, that has created some like something that has created some disturbances in the image capturing, right? But somebody's eyes can be more penetrating, or could be more, can be better. And so they can recognize the difference between a very high quality image and a slightly modified image, right? So what I mean to say that human perception level is also different. But in general, there are measures that have been used to evaluate a model. Several measures are used to evaluate a model's performance, that how different is the original data samples that are coming from. Like we do not have the original data distribution, but the samples. Let us look at the sample distribution, or that we call as an empirical distribution. Like how many images of pink color flower, how many images of white color flower, how many. So this is an empirical data distribution. So we actually find out the distance between empirical data distribution and the data that is generated from the model. So if there are 5,000 images that are generated from the model, and you have 5,000 data samples, you would like to see what is the difference between these two distributions. That is how you find out. Okay, so the difference is also defined in terms of like fidelity parameters are there, inception score is there, and then we have several parameter evaluation parameters that are defined. over the time period. So the same text, I can say that this is a good text, summary is good. Someone may say that, no, this summary is not good. So they may justify, the humans can justify that why it is not good, why it is good. All right. Any other question that you have in your mind? So in total, diffusion models are very simple. Add noise in T steps and use a network to remove noise in T steps. That's all. And it's a very simple model, right? Thank you, Prathamesh. So idea is basically very simple idea that is taken from, like, when we are adding noise, there's some kind of like equilibrium that is disturbed, of arrangement of things like your jigsaw puzzle. We are simply removing every connectivity, and then we want to come back to the original, right? The equilibrium state. So that equilibrium state, how do we attain? By putting, like, we can say that the ensemble of non-equilibrium state, a change in the energy, like you can say that change, like free energy, you can say. How do we express the free energy at each step in the non-equilibrium stage? We take the ensemble of that and equate to the to the difference in say energy level uh, at the between the equilibrium state A to equilibrium state B, when the things are in thermodynamic equilibrium. Idea was taken from there, and that was an initial idea given in 2015 paper. What are the Chandrakant Srivastava is asking, what are the practical uses of technology? Um, Practical uses are many, because sometimes you want to generate images that, from occluded space, like you see in CCTV camera, you want to identify, say, criminals. They're occluded, their faces are hidden, or they are trying to hide their faces. So that is one application. The in Like in sometimes when we are trying to figure out MRI images, there is something that has, like, some vibration has occurred, because of which see, old age patients, it is very difficult to take MRI images because there's some internal vibrations that are more in human body. And so how do we create more crisp images to understand the MRI, through MRI signals, to understand the state of the body of a patient? That can be another example. There are many other examples, like two of my interns right now are working on gene expression analysis, and I have requested them to apply uh, diffusion model for data augmentation, because gene expressions are very few in number, and we want to analyze gene expression for cancer detection and grading. So there are several examples. Can this be used in power systems, a substation for fault detection and identification? Fault detection is a classification problem. Identification is also a classification problem, Chandrakant Srivastav. If you do not have enough data, you can make use of data augmentation technique, make use of diffusion model. So that is there. Here, generative models are like, sometimes, fault detection is so difficult to understand because of the complexity of the system, that it is better to generate the entire, like, system uh, as uh, as a system of n inputs, and what all states it can undergo. So under different states, if there is a state change in which anomaly is detected, so this generation of different states, which we have not visualized as humans, that can also be done. That is what I believe is possible. Uh, cell. Very. What is Lakhan Lal is asking, I could not get this. Can be used in image generation quality much better than other attention. See, here they have used in cross attention model. Attention is only a, say, small tool that you can apply to improve the learning, representation learning method of your network structure. So it is learning features. Any network is learning features. By applying different attention models, you can make trial and error, use trial and error method to find out which kind of attention model suits best to your data. Yes, depends on data as well. Thank you. Thank you, everyone. So if there are no questions, I thank all the people, especially those who were interactive. So that keeps the session alive.
Thank you, ma'am. Thank you so much, ma'am, for taking the time to share your incredible insights, experiences with us today. Your journey and contribution to deep learning and computer vision are truly inspiring. We are deeply grateful for the knowledge you have imparted and the motivation you have sparked in us. It was an honor to learn from you, ma'am. Thank you so much.
Thank you, Lakhan. Thank you, everyone. Have a great day. And in the afternoon also, we are going to have a good session. Please do attend that. Thank you.